We're gonna talk about differential equations and slope fields today. Start with the warm-up. This is way back when we were talking about like related rates and all that stuff. So we're gonna take it with respect to x, and so when we do the y, we're gonna have that y prime, and you can write it the way that you would like, but just remember here, this is a product rule. And what we're going to do is we're just going to solve for y prime. And I know some people do like to write it dy over dx. I prefer y prime, but you can do whatever makes sense to you. I'm just going to put all the y primes on one side. And I'm going to move everything else to the other side. Minus 6x. Factor out that y prime, and then I will divide it to get the y prime by itself. And remember, y prime is our slope. That's going to be pretty important for what we're doing today. We're evaluating this at the point 1, 1. So that's really nice. We have 3 minus 6, negative 3, minus 2, negative 5. And 2 plus 12, 14. 14 minus 8, 6. And my answer will be A. Number 2. F is a twice differentiable function with the horizontal tangent at line x equals 1. So I'm going to write that real quick. That means it's 0, right? F prime of 1 equals 0. It's going to help us. As shown in the diagram above, which of these statements must be true? We know my f prime of 1 equals 0. That's probably going to be in the middle. F at 1 is some unknown, but it is a positive y value, as we can see it's above. So this is some, we could call this 2, but it's some positive y value. And then it is a concave down. Remember, concave up means the second derivative is positive. So this is concave down, which means it's negative. Second derivative is going to be a negative number. And again, it doesn't matter what that number is. All we need to know is a positive or a negative. What that means is, let's look. So my smallest value, sorry. And f of 1. And we look, and our answer will be E. So this will be a negative number. This will be 0. This will be some positive number. And then the last one, let f be a continuous function on negative 4, 12. If f of negative 4 equals negative 2, f of 12 equals 6, then the mean value theorem guarantees that, blah, blah, dot. So what we're doing, the mean value theorem is this. F of 12 minus f of negative 4, and then we do f minus negative 4, plug in the things that match. 6 minus negative 2, and I'm just going to do a quick solve. The reason I'm doing f of c is because I see this in the answer. 6, that'll be 8, and then that'll be 16, 1/2. Okay, so with that information, let's look at it. So it's some continuous function. Let me just make a little sketch. I don't know what the function is. I don't really care what the function is. But we say from, let's say this is negative 4 and this is 12, 6, negative 2. Cool, great, some continuous function. Well, if it was the intermediate value theorem, I mean, it's not, but it would apply a little bit differently. Let's see, mean value theorem guarantees a slope. Let's see, I guess I'm gonna get rid of this. So we found it equals 1/2. Okay, cool. Fantastic. I can't do this because I don't know the slope is at that point. I can't do this one because this is it's not given to us. We don't know that. This one, it could be, but that's not. And that's intermediate value theorem. If we look way back in our notes. We can see that the intermediate value theorem and all those lovely theorems, that's not really what we're looking for. We don't know that one. So we're going to just end up with C. And we say that intermediate value theorem and all those lovely theorems and stuff, those are the ones that kind of pass through. So there's an intermediate value between it where it passes through. And that really doesn't apply to us right now. So guess what? Doesn't really matter. So we're only being asked the mean value theorem, which is the instantaneous slope between 2 points. And we can move on. Okay, notes. There is a whole class called differential equations. It's called Calc 4. Some schools just call it DiffEQ for short, but we're just going to cover very, very simple differential equations today. And we're going to call them first order separable. And this is going to be what most of our entire unit is going to be about. So a differential equation, an equation which contains an unknown function and some of its derivatives. In other words, an equation with both y and y prime in it, or y double prime. An example of this would be like the one we just did for our warm-up, where it has that y prime where we had to solve and do all that stuff with respect to x. And I always like to put a little example in there. The order of a differential equation is the highest derivative in the equation. So this would be a second order differential equation. Yep. All right. So today our goal is to show that a function y is a solution to a given differential equation. And don't let this fool you. It looks scarier than it actually is, but all we're going to do is we're going to just take the derivative, and we're going to make sure that it fits in here. So take the derivative y prime, negative 8 e to the negative 2x, right? Nice and easy. Okay, so now we have y prime. And then we have negative 2 times whatever that y value was 4 e to the negative 2x. And, oh my gosh, look at that. It does work. Obviously, this is a very simple one, but that's what a differential equation is. We've already kind of seen them, so it's going to be hopefully not too bad. Example 2, show that y equals c e to the negative 2x is a general solution to the differential equation y prime equals negative 2y. Let's take the derivative. And c is just some constant, so it doesn't really matter at this point. Okay, fantastic for us. So we want to show that it is a solution. Whatever my y value was, which was this. Oh, there's a negative 2. My bad. There it is. I was wondering, I was like, it's not going to match. It should match. Not all the time, but these ones. And look at that, they match. And we're kind of, remember when we were doing like that plus C and stuff like that? That's like kind of what we're talking about today. The entire family of works as a solution. I'm going to do SOL for solution. And basically what we're saying is we're kind of finding those like functions. Let me put it up here just a smidgen so I don't run out of where we have like the plus C. We're entire family for this one. Obviously we have a C because it can be any constant wherever, is going to satisfy this general solution. So whatever that C value is, if it could be -1,000,000 or 2 or 8 will be satisfactory in our differential equation. When we take a general solution and solve it for a particular condition, we call this a particular solution. Much like when we use the initial condition to find the value of plus c of an antiderivative. So what we're doing is we're just basically being like, hey, we're going to actually be given a key piece of information to use to solve. So right when we had some function, it would be whatever, I don't know, something plus c. It's going to be like that. We're kind of doing that. Now we got example 3. Show that y equals a sine of x plus b cosine of x is the solution to the differential equation y double prime plus y equals 0. Great. Just a lot of derivatives. And this one, just the hardest part of this one is literally just going to be watching those plus and those minuses. And if you get to a point where you find that it does not work, maybe check your math and make sure that you are in the right place, because that's usually what happens, is just putting it in wrong place, making sure that there's not a negative where it shouldn't be a negative, and all that lovely thing. All right, plus our original y value. And you should see pretty much off the bat that these are going to cancel out and equal 0. And it works. These are very, very easy, simple ones, just doing derivatives and making sure it plugs in. And this would be just stating any a and b are constants of that could be literally any number, right? It's just like our plus c. We don't know, it could be 2, 4 million, but for our just these examples, these are just going to be constants. Now we're going to get to actually dealing with an actual initial condition. What we have is y equals 1 plus c e to the t over 1 minus c e to the t as a general solution to the differential equation. Y prime equals 1/2 y squared minus 1. Find the particular solution that satisfies the initial condition of y0 equals 2. I'm going to rewrite this. I always like to write it in my own handwriting. Usually helps me figure out what I'm gonna do. We are given an initial condition. Fantastic. So now we're gonna find a particular solution. Let's see. Let's just make sure it satisfies y0 equals 2. I'm just making sure it works. Don't take them at their word. What if they're lying to us? They usually aren't, but remember these equal 1. And now we have to deal with those c's. We have 1 plus c, 1 minus c. I guess it looks a little unclear. I did not mean to have the c's involved there. The c's are separate. And then we're just going to do some simple algebra. Okay, fantastic. Good for us. Now we found our c value. Now that was given our initial condition, so we can find a very specific thing, and that means we're going to plug that back in to our y to find the specific function because it was given to us. E to the t. Oh, minus. And we're done. Now we're gonna do some slope fields. Slope fields aren't super common. You might see one on the BC exam. You're more likely to see them on the AB part because we have a lot of BC topics to cover. But fill in the table provided with values of y prime and sketch teeny tiny tangents with that slope on the graph provided. Several y prime values have already been calculated and sketched to save time. This can be a lovely there's a computer program. Obviously, it's going to be nice and easy. So we have just plug in all of our values. I'm just following, right? Just plug them in. We're given an x and y value, so it doesn't really matter too much. And then this will be 1, 2. Zoom out. We're just plugging that into this function right here, right, to find the y prime. I just like to rewrite it equals slope. And I'm going to graph them now on my graph. So -3. And we're gonna have to schedule a little bit. Might be good just to put it like kind of like that. 0 slope. And then 3 is gonna be pretty steep. And then we go into, I'm just literally graphing these on the line. I'm putting the slope of what it is, right? 0, -2. And I'm writing these just solely because it's kind of gets a little messy. And this will be -1. Okay, fantastic. Okay, we graphed all those lovely little slopes. These are tiny, teeny tangents. And now, using the slope field, graph the particular solution to the differential equation with the initial value y0 equals 1, and then we have another one through the point -2, 1. Okay, I'm going to color coordinate these. Make our lives a little bit easier. So we have purple and we have green. All right, so what we have for this one, let's see. So 0, 1. So it's probably going to be here. And we're just going to kind of like follow the lines a bit. I'm not super, I don't like that too much. I'm not super picky about kind of doing it. Yeah, it looks a little too steep. Some teachers are much more picky about this. I'm not super picky because this is BC Calc and I'm not too worried about super accurate slope fields because it is just guiding our function. And then let's do green. So -2, -1. Okay, that's a 0. And let's see, we're just gonna kind of follow some of our, that's gonna go up. Something like that, I guess. Not gonna be super nice and neat, but there we go. That's about what a sketch would look like with a slope field. We're kind of just following the slopes with our function. We're given an initial condition and we kind of just trace along of where the slope is kind of like a current, like we have to follow the current. And then some notes on the back, just boring notes. Any curve that you draw on a slope field is a particular solution to the differential equation, which is used to generate the slope field. Once you have it, then that curve is a particular solution, but it can be anywhere on there, depending on what the function is. Each one of the curves that can be drawn on the slope field is part of a general family of solutions. What that means is like, I could have this graph that, you know, is right here, and our particular solution is 0, 1. Well, let's say we did -1/2, -1/2, or something like that. It still kind of follows. It's still going to look pretty much the same. It's just, you know, shifted, right? Because we have a different particular solution. Like this one is going to just move. It's about the same. My sketches aren't very great, but this is what it looks like. You can also, there is a link right here if you would like to look at more slope fields. We're not going to get too much into it, but This is the key. Actually, let me just do just one. So there are a couple that could be correct. And what we're going to do is just kind of look through them and find what that means. So we already know that number one is E, but I always try x1, y1, -1, -1. You can try some zeros. I usually try to stick away from zero because sometimes we get like this where it's like, not great. And if you wanted to, you could try to figure out what the antiderivative is. For this one to be like x squared over 2, right? But we don't really know that. It's more of just kind of using that function to figure it out because it could be a couple of different things, and we're just going to look at what we have. So we got number one, E. We have y prime equals x, sorry. So wherever that x value is, that's what the slope should be. So it should be pretty much the same, like this. Like wherever the x value is, then the equals the y prime. So if my x value equals 2, then my y prime is 2. So on every single place on my x equals 2 line, I'll have a slope of 2. And that's why it gets a little tricky is we have a few different options of what it could be. So it could be A, right? These look pretty much the same. Let's see. B is a no, C is a no, D is a no, E. Well, we know E's the answer, but I'm just giving you options. This one's a no, no, yes, no. So now we have a few A, E, and G. Yeah, A, E, and G. And they do satisfy, but they might have other ones that are more satisfactory. So let's look at number 2. Y prime equals y, which is kind of the inverse of what we just said. So everything across your y value will be exactly the same. So C works. It looks like F works because we're going this way. So if y equals 2, then y prime equals 2. So then it'd be like this, and all that lovely stuff. That's what I'm looking for. F, H. Okay, cool. And we're just gonna keep going through. I'm not gonna do all of these, but I'm just showing you there's a couple of solutions that might be correct, but one might match a little bit better. So let's look at number 3, and then I'll let you finish the rest, even though I know you have the answers, but walk yourself through them. Let's see. F is 2y. So whatever my y value is, it's gonna be double that. Okay. So let's look. So I could do 0. I might want to do 0. So if y equals 0, then our y prime is going to be 0. So we have B, C, F, and H that are all possible ones, just for the initial one that I just selected. Let's do y equals 1. So everywhere the y equals 1, that'd be a slope of 2. Okay, well, we get rid of B. F looks good. I feel like this looks more like a 1 for C instead of a 2, so I'm gonna get rid of that one. And then this one, H, I already know that's the answer, but this looks like a half and not a double. So my only answer for that one would be F. And that means we can get rid of this one. We can kind of trial by error and just go through these and figure out what's the correct one. And there we go.